In section 3.9, we're going to look at logarithmic functions. We're going to determine the inverse of an exponential function, so the relationship between logs and exponentials. We're going to identify some properties of the graphs of a logarithmic function, and we're going to graph the natural logarithmic functions. In the first example, we see some data here talking about the relationship between average walking speed and the population of a city. And so in this data set here, we can see that as the population increases, it looks like walking speed increases. If I connect these dots, I just want to see what this pattern might look like. So there's this slow increase where it's increasing, but not by tons each time. So it increases a little bit faster at the beginning, and then a little bit more slowly over time. So does this data appear to be linear? No, and no, because the amount of increase is not constant. The rate of change is not constant. And does the data appear to be exponential? No. So exponential would be, so linear would have been a straight rate of change. Exponential would have been increasing more and more rapidly. So the rate of increase is not increasing. This appears to be doing the opposite. The rate of increase appears to be decreasing. So this data is actually logarithmic. And a logarithmic function is going to be the opposite of an exponential. The rate of increase does not increase. The rate of increase decreases. So this is one little taste of what the shape of a logarithmic function is going to look like. So now we got to get into some more details before we go back into the data and before we're ready for logarithmic regression. I'm going to think about what the shape of a logarithmic function will be. Okay. So we are going to be looking at the general form of a logarithmic function being y equals log base b of x, where b is the base, x is the input or argument. I often use the word argument. And the output, y, represents the power of the base b that you have to raise x to. Like I said, I usually call it the argument that gives y, which is the power. All right. So evaluate log base 10 of negative 100 using my calculator. Okay. So I don't have to type the little 10, but since they did, I will go ahead and do so. And it says undefined. What do you observe? Does it seem reasonable? Explain. Okay, so it's undefined. Is undefined. And remembering what this question is asking us, it's asking us what power of the base, which is 10, is negative 100. And I cannot raise 10 to a power and get a negative number. If I raise 10 to the first, 10 to the second, 10 to the third, it's going to be 10, 100, 1,000. If I raise it to the negative power, it's going to be 1 over 10, 1 over 100, 1 over 1,000. But I'm never going to get a negative, okay? So I can't get a negative argument. So we're not allowed to have negative arguments. All right, so we'll emphasize that. The argument cannot be negative. What about log of 0? All right, I guess they wrote it without the 10 this time. Same thing. Also undefined. Okay. So again, they're asking the question, what power of 10 is 0? So even 10 to the 0 power would be 1. I can't get 0. I can get small. 10 to the negative third is 1 over 1,000 or 0.001. I can go 0.0001 if I make the power large enough negative, but I can't get to 0 itself. So this is also undefined because no power of 10 will equal 0, right? Because 10 to the negative fifth, for example, equals 0.1, 2, 3, 4 zeros and a 1. So I can get close to 0, but I can't get to 0. As my reason. They can get close to 0, but not actually 0. And so, again, the argument cannot be 0. Argument can't be negative. The argument cannot be 0. Okay, so what is the domain? They asked us these questions to try to help us figure out the domain. I know that negative numbers are not in the domain. I know that 0 is not in the domain. I know that I can have any positive, whether it's a small positive. I could have small positives inside the logarithm, like 0.001. I could have large things. I just cannot have negatives inside the logarithm or 0. So that means that I'm going to have strictly greater than 0. So I'm going to have x being strictly greater than 0, or parentheses from 0 to infinity. Depending if I want to write this in inequality notation or interval notation, I get to choose, but it can't be 0 itself, so I'm not putting a bracket. It's got to be a parenthesis, no equal bar on my inequality. What is the range? Remember, the output y is an exponent, so they give me a hint. So if I put in very small things, so for example, if I do log of 0.001, that's going to give me -3. So I can get negative things out. Or I can do log of 100 and I'll get 2. I can put in really big things and get positive things out. I can put in a bigger number and get a bigger positive, of course. So I can get negatives, I can get positives. I can even put 10, I can put 1 in and I can get 0. So I can get 0 out as well. So the range is going to be all real numbers. Or if you want to write that in interval notation, the interval from -infinity to infinity. So I can only plug positive functions in for x in the logarithm, but I can get any value out of the logarithm. All right, tables. We've got two functions. One of them is going to be f of x equals 10 to the x. The other one, g of x, is equal to the log base 10 of x, so just log of x. And I'm going to make a table first for f. And we're going to plug in -2, -1, 0, 1, and 2. So these numbers are going into the function 10 to the x. So 10 to the -2 is 0.01, then 0.1, then 1, then 10, then 100. Okay. Now if I plug the other values into the function g of x, if I plug in plug in 0.01 into log of x, I get -2. If I plug in 0.1, I get -1. I get 0, I get 1, I get 2. Compare the input-output values for f and g. So the inputs of f are the outputs of g, and vice versa. The outputs of f are the inputs of g. So they are reversed. Okay, and then it says graph the two functions. So They're kind of already graphed. I'm going to turn the dots off. And do they want me to graph y equals x? Yes, they do. Also graph y equals x, because what we're trying to show is that these are inverses of each other. So we've seen it from the table already. In the table, when your inputs and outputs flip from one table to another, you know the two functions are inverses. Now graphically, we can see the symmetry between the exponential function and the logarithmic function right here. So we have that symmetry as well, graphically, showing us that they're inverses. Okay, so describe the symmetry. So they are symmetric across y equals x. All right, so they are talking about why these are inverses. So the results demonstrate that those two are inverse functions. Finally, they want us to use the algebraic approach demonstrated in example 1 to verify, that our two functions are inverses. And that would be switching the variables and then swapping x and y. I had to look back at example 1. Okay, so if I have my y equals 10 to the x, we're using the property that b to the y is equal to x is interchangeable with log base b of x equals y from the last section. So if I use that property on this function right here, I'm going to switch this into the log base 10 of y equals x, right? And then interchange the two variables. This makes this log base 10 of x equals y, and that is back to the same thing as our other function. So algebraically, via that property, demonstrates that the two functions are inverses. Okay. Common properties of logarithmic functions. So first of all, the domain is all positive real numbers or x greater than 0 or 0 to infinity, however you prefer to phrase this in inequality or interval notation. The range is all real numbers. So again, you can phrase that in interval notation if you prefer. And then the inverse is defined by 10 to the x, now if it's log of x. Now, we can get a little more general than this. And so if you had f of x equals log base b of x, then its inverse g of x is going to be b to the x. Whatever the base of your exponential is, that's the base of your logarithm and vice versa. All right, so we're going to look at the graph of the natural logarithmic function. So let me make this one just natural log of x. We're going to plug in 0.1, 0.5, 1, 5, 10, 20, and 50. All right. So negative 2.30, negative 0.69, 0, 1.61, 2.30, 2. Actually, it's 3.0. If I round it to two places like I have been, it would be 3.00. And then 3.91. Sketch the graph. Okay, I got to get rid of some of my other graphs. We're just all right. So there's this graph. Okay. looks something like this. What we should know about this is that it's a slow growth, so it starts off growing rapidly and then the growth slows as it goes further to the right. Okay. What are the domain and range? Well, the domain, since that graph did not go into the negatives on x, the domain is going to be 0 to infinity. And the range, it went down, it went up, so the range is negative infinity to infinity. So the things we observed about log of x are going to be true of natural log of x as well. Determine the intercepts. Okay, so there was an x-intercept at 1, 0, and there are no y-intercepts. Does the graph have a horizontal asymptote? No, there's no horizontal asymptote, but it does have a vertical asymptote. And its vertical asymptote means that it's heading down towards this line instead. So it has a vertical asymptote instead. And because this is the inverse of an exponential, even the asymptotes are opposite. Exponential functions have horizontal asymptotes. Logarithmic functions have vertical asymptotes. All right, new table. I already had a couple of these values. So 1, 0, then 0.5, negative 0.69, and I gotta put in some new ones. Oops, how was it? Oh. Negative 1.39, negative 2.30, negative 4.61, and negative 6.91. As the inputs take on values closer to 0, what happens to the corresponding outputs? So they become larger negative. So if I made them even, I'll push that up, become larger negative numbers. If I made it even closer to 0, 0.001 or 0.0001, they're getting bigger and bigger. It's not happening super fast, but they will get bigger negative. There's no limit to the size that they'll get as long as you just make this number even smaller and smaller and smaller. And so again, as we were mentioning before, that defines that vertical asymptote on the y-axis, or the line x equals 0, for the graph of the natural log function or any logarithmic function. All logarithmic functions are going to have the same vertical asymptote, similar to the way that all of our exponential functions in standard form had y equals 0 as their horizontal asymptote. All right, so generally, the vertical asymptote is the vertical line, x equals a. The function becomes very, very close to it whenever it touches. As the input values get closer and closer to a, the output values get larger in magnitude. And it could be larger positive or larger negative depending on if your graph was reflected. So graph e to the x and natural log of x and y equals x describe symmetry. Okay, I'll get rid of my table. I already have natural log of x, so we'll just graph e to the x. And then we need y equals x as well. And I'm going to zoom home just because my scale is a little funky. I can see symmetry. Again, just like the 10 to the x and the log of x, e to the x, natural log of x are symmetric. They're inverses of each other across, graphically across y equals x. Okay. All right, use our algebraic approach to show their inverses again. That algebraic approach relies on the fact that b to the y equals x is equivalent to the log base b of x equals y. So if I take y equals e to the x in exponential form and switch it into its equivalent logarithmic form, that's going to be log base e of y equals x. Then we switch the variables. I'm also going to shorthand log base e to ln. And so this shows that the inverse is natural log of x. Oftentimes, I write natural log of x in cursive. Sorry if I just snuck that in on you, the ln of x instead of ln of x. Don't know why. It just keeps the function together. So I accidentally did it in handwriting. So I'd mention that. Sometimes I do that. All right, now we're going to do some shifts. Okay, so we did this a little bit in the beginning of cluster 1 when we were talking about the exponential functions. We had some shifts, and those shifts change where the asymptote was going to be. So we're going to have some shifts here that change where our asymptote is going to be as well. All right, let me get rid of e and y equals x, and let's look at our shifts. So I'm going to graph y equals natural log of x plus 3. So that seems to have shifted the graph to the left. And so where the vertical asymptote used to be x equals 0, let me dot it before I move it. All right, it's not at 0 anymore. It got shifted left 3. So -3. And so my asymptote's now at -3. I'm going to get closer and closer to the input -3 as my outputs get larger and larger. Okay, so the vertical asymptotes equation is going to be x equals -3 here. And if I change it to an x minus 2 inside the parenthesis, now I got shifted to the right 2. And so now I will have x equals +2 as the vertical asymptote. So it's not always at x equals 0, but the only thing that would cause it to be somewhere different are these shift values inside the logarithm. Those additive or subtractive values are shifting either left or right and moving the vertical asymptote.